Since the Big Bang, almost 14 billion years ago, the universe has been evolving. In the furnaces of a million billion stars, the atoms that make us were forged. Every piece of us began in the heart of a distant star.
The sun, like many stars in the universe, has its own natural variability. It has a heartbeat. So on timescales of years, there are things happening. And on periods of weeks, there are things happening. On periods of milliseconds, fractions of a second, we see things happening. So our understanding will be driven by technological development.
Today, humanity has literally launched itself on a voyage of discovery into the cosmos. And Irish investigators have been playing a key role in this adventure since the dawn of the space age.
I think what happens when you push frontiers of knowledge is that you have to develop new technologies. And what we see from the space programs and space exploration is that those new technologies find new applications on the ground. So there is an overall benefit to society from pushing the frontiers of knowledge in astronomy and space.
Definitely it's important for Ireland to be involved in projects like this because it's cutting-edge technology and it always will give us an edge over the rest of the world, really, when it comes to science and technology.
Europe's space programme is one of the biggest and most successful in the world, and Ireland was one of the founding members of the European Space Agency. Irish scientists and engineers have played a part in every space mission that Europe has launched. Europe is also leading the way in some very dramatic missions that are designed to explore the most extreme and violent events in the universe. Irish investigator Lorraine Hanlon is part of a team that has detected huge explosions of radiation known as gamma-ray bursts.
What's really exciting about gamma-ray astronomy is that these sources light the way back to the very first star that switched on in the universe, and that's what we want to see with Integral and with other gamma-ray astronomy missions.
Lorraine Hanlon has travelled to the outskirts of Madrid, to the European Space Agency, to meet with colleagues and update them on her latest findings. Hanlon's area of expertise involves the study of light sources in the galaxy, and in particular, these vast radiation bursts that are invisible to the human eye.
My work is all about looking at the universe in different colours than what we can see with the naked eye, which really is a very narrow band of information that the universe presents to us. And if we want to get the full picture of what's happening in a galaxy or a cluster or a supermassive black hole at the centre of an active galaxy, we need to have the full range from low energy microwaves all the way up to very high energy X-rays and the highest energy gamma rays such as Integral can detect. Light that we see is actually made when little particles that are called electrons wiggle. But that wiggling can produce light at even higher energies than we can see with our own eyes. So if you have these little charged particles which are really being pushed and pulled very violently, they produce much higher energy rays which are called gamma rays. So when we study gamma rays in the universe, what we're really looking at is the most violent, most energetic processes that are happening in the universe.
Gamma-ray bursts have been one of the greatest mysteries of modern science. They often release as much energy in a few seconds as the sun will generate in its entire lifetime. Hanlon believes they're formed by processes whereby supermassive black holes swallow matter in the centre of galaxies. The violence of these events creates a huge outflow of particles. This frenzy of energy release will result in the production of the gamma-ray bursts. In the mid-1980s, a group of scientists came together and proposed to the European Space Agency a new gamma-ray astronomy mission. This led to the construction of Integral, a space telescope specifically built to study the huge range of light sources in space. It was successfully launched from Baikonur in Kazakhstan in 2002. Integral will continue to operate until 2012 and has proved a vital resource to Hanlon and her team.
This is a 1:10 scale model of Integral, showing here the solar panels, obviously, to power the spacecraft. Here's the spacecraft bus, as it's called, which hosts things like the memory, the processing power. And then sitting on top of the bus are the scientific instruments that would have been built by institutes in the member states. So here we have the main gamma-ray spectrometer called SPI. Up at the back here, this instrument here is called EBIS, the imager. There are two X-ray telescopes here, GEM-X, and then here is the optical monitoring camera, the OMC, for which Ireland was a partner in construction. And so the idea is that we have full coverage of the same targets that the main instruments are pointing to at gamma-ray energies in the X-ray and the optical. So we can look at the variability of these unusual sources across all different energies.
Technology provided by a number of Irish institutions is playing a key role in the Integral mission. Its ability to see far into space means that it's allowing investigators like Hanlon peer into the distant past.
If you took a snapshot of the sun, you're not seeing it as it is right now. You're seeing it as it was 10 minutes ago, because that's about how long it takes the sunlight to reach us. So you can move that process further and further away in time and space. That's what Integral is. It's a time machine, because it allows us to see events that happened very far away, which means they happened a very long time ago. The first gamma-ray burst we've detected happened when the universe was very young, maybe 1.5 billion years old. So I think Integral has made a huge contribution, because it allows a window to early time, to the early universe.
Lorraine has been one of the most productive and most efficient observers of gamma-ray bursts with Integral. So as soon as the mission was up in space, she and her group proposed to look at these gamma-ray bursts with Integral data. And they've been very successful. They've become maybe more and more successful over time, because this group has been publishing some of the most important results and has expanded our knowledge. This group is leading truly on an international scale.
Almost, yeah. What I see Integral's main contribution is, because it has this fantastically sensitive detector, that it's been able to unveil a population that we didn't know existed in our own galaxy. And now suddenly we have knowledge from Integral that there are hundreds, many hundreds of probable black holes strung along the central disk of our galaxy. The sheer number that Integral has picked up is pretty astounding, 400 plus. And I think that shows us that we have a long road ahead of us, and a very exciting road, to really understand what process drives black hole creation and how many are out there, and opens our eyes to what gamma-ray astronomy can be in the future.
While gamma-ray bursts allow us to observe the violent death of stars billions of years ago, another Irish investigator is more interested in the tumultuous life of a normal, middle-aged star, the one which we call our Sun. Peter Gallagher of Trinity College Dublin leads a team that observes the violent processes of the Sun and the effects that these have here on Earth.
My research group focuses primarily on solar activity. We're interested in explosions on the surface of the sun. We want to try and understand what the basic physics is, what the driving physics is of these explosions on the surface of the sun. Now, once these explosions occur, they eject material, electrons, protons, radiation out into space, and that radiation can sometimes then travel to the Earth.
These huge eruptions of material from the surface of the sun are called coronal mass ejections. They are enormous streams of energy that would kill everything on Earth were it not for our planet's magnetic field. Mostly they're harmless, even beautiful, but not always.
Well, there's a number of direct consequences that these eruptions have. The first is the Northern Lights. This is the spectacular, beautiful greens and reds that we see at the North Pole and at the South Pole. Another effect that they have is on satellites. Satellites are out in space, they don't have any shielding, and these electrons and protons can damage the electronics on board the satellites. So telecommunications can drop out. We can also have GPS errors as well.
Gallagher and his team are involved in 2 space missions that are shedding new light on the physics of the sun, which is how this Irish investigator hopes to improve the forecasting of what he calls space weather. Accurate space weather forecasting is essential to predict when and where the sun's ejected radiation will strike.
For about 10 years, I've been working on the SOHO spacecraft, which was built by the European Space Agency and is now operated by NASA. This is a mission which really has revolutionized our understanding of the sun. It enables us to take high-resolution pictures of the surface of the sun to see what's going on the surface, but also it has detectors on board which enable us to sample the wind from the sun as it passes by the spacecraft on its way to the Earth. So it acts as a sentinel, sitting in space, monitoring what's coming from the sun and ultimately what will hit the Earth.
Gallagher is also collaborating with NASA in the United States in its ambitious new space weather project, STEREO.
The STEREO is a $500 million spacecraft. They have launched 2 of them. One is ahead of the Earth and one is behind the Earth. And they give us 2 perspectives, like our eyes, give us 2 perspectives on what's happening on the surface of the sun. And they can tell us the direction that explosions are occurring at on the surface of the sun. So they tell us where they're coming from and where they're going with a much greater accuracy. We're going to be able to finally tell you that there will be bad weather on a given day to an accuracy of hours.
The contributions of Irish investigators to the European and American space missions have been well established, according to Irish space industry commentator Leo Enright.
Peter Gallagher's work on solar physics is important for things like telecommunications and for the power grid. But if you want to see a real practical economic application of space research, you need to look at the technological developments that we see here in Ireland that have had genuine economic and social impacts.
The Tyndall Research Centre in County Cork was one of Ireland's first space technology centres, and it's an example of where the benefits of successful projects can be brought back down to earth. While Gallagher, back in Trinity, has been looking at where the sun's radiation will strike, investigator Brendan O'Neill has been developing a way of recording accurate measurements of the levels of radiation that astronauts and satellites are exposed to. In the process, he has found ways of helping in the treatment of cancer patients.
In about 1987, we were doing some work with the European Space Agency. One of the things they had an interest in was looking at the amount of radiation that their electronics were seeing when they flew satellites in space. And it's important because all of the solid-state electronics are very sensitive to incoming radiation, and the incoming radiation can cause the electronics to fail. So one of the things that they really wanted to do was have a measure of how much radiation their electronics were seeing. It's a fairly well-known phenomenon that the electronics are sensitive to radiation. You can actually use that as a measurement of the amount of radiation. And normally what people who are building these integrated circuits are trying to do is make the electronics radiation hard so that they're not affected by the radiation. But one of the things that we're able to do is that you can actually make the electronics radiation soft, so you make them more sensitive to the radiation.
O'Neill has taken this technique and produced an electronic device that is receptive to radiation rather than hardened against it. The detector is called a RadFET, and it can be placed beside the electronic systems aboard a satellite to accurately monitor radiation levels.
RadFET is a very small transistor. Radiation hits the structure of the RadFET and changes one of the basic parameters. This is called threshold voltage. Threshold voltage will change with radiation dose. By measuring this change, you can get an information about the received radiation dose.
While RadFET devices are now standard equipment on European space missions, they're also a dramatic illustration of how technology developed for space can be adapted as a life-saving spin-off back here on Earth. A detector that can monitor the radiation on a voyage to Mars can also be used to monitor the radiation delivered to a patient who's being treated for cancer.
The main way that we treat cancer is to use a combination of surgery, radiation therapy and chemical treatment. Radiation therapy uses X-ray treatment so that you can focus the beam on the tumour and that kills the tumour. Because of the advances in technology, the size of the aperture of the radiation beam is becoming ever smaller. So it's very important that you're pointing the beam in precisely the right direction. And one of the ways of checking that is to have a device that can allow you to measure on the surface, as the beam goes into the patient, that the right amount of dose is being received at the right part of the surface.
So this is the one-dose product. It's just used for a single dose of irradiation. The one dose is almost like a stick-on Band-Aid. The device is peeled off. You actually put it on the patient's skin close to the point being irradiated. And then after the dose of irradiation, you simply take off the device, you plug it into the back of the reader, and you get a direct readout of the radiation recorded for that single dose on the skin.
As we make our treatment more and more precise, we have to be sure that we're actually delivering what we think we're delivering. And so a lot of the new machines, such as this and some of the other products, have built-in scanners that take pictures to make sure the radiation is going where it's supposed to go. But they don't measure the amount of radiation in those locations. And this device is capable of measuring the actual dose as the radiation beam goes into the patient, and you can check that measurement against what your computer system thinks it should be. We know that this is a very reliable device, it's very easy to use, and therefore will have widespread clinical applications and will help us to become ever more precise in the delivery of treatment. And what this means is, from the patient's point of view, that there's an enhanced prospect for survival with a reduced prospect for a complication of treatment.
The European Space Agency is developing missions that aim to travel to the further reaches of the galaxy, bringing spacecraft to previously unexplored planets where conditions are far beyond our experience here on Earth. Investigator Donagh O'Mahony is looking into new materials that can withstand a range of extreme conditions.
The European Space Agency are planning to launch a satellite to travel to planet Mercury in the year 2013. This satellite will take up to 6 years to actually reach Mercury, and then it will spend 1 year orbiting Mercury. And because Mercury is the closest planet to the Sun, the temperatures that they expect the satellite to experience will be up to 350 Celsius. So we've got to build components that are going to last for 1 year orbiting the planet at that kind of temperature. Now what we're trying to make is a power switch that will be used on the solar panel of this satellite.
At present, the power switches on a satellite's solar panels are made of silicon. But silicon has a fundamental limit to its operating temperature.
Once you hit about 250 Celsius, things start to go really belly up. So the European Space Agency, purely from a contingency point of view, have to look at other options and other materials.
Silicon forms the basis of 90% of the world's electronics. It's used in computers, televisions, stereos and mobile phones, and it's cheap, high quality and is readily available.
But silicon has its limits, especially at high temperature. So you can imagine if you put something like this into an oven at 300 Celsius, it's not going to survive for very long. So for about 10 years or so, we've been working with new electronic materials known as wide bandgap semiconductors. So this is silicon carbide. It's the second hardest material known to man. It has an extremely high melting temperature and can handle extremely high electrical powers as well. Now, these materials have really only come to the fore in the last decade or so, and they're used in blue laser and blue LED technology. So you might know the Sony Blu-ray device uses gallium nitride devices. Now, we spotted a number of years ago that these devices could also be used in a high temperature application. So for the past 2 years, we've been trying to divert our group's focus towards building devices that can operate at very high power and high temperature.
The Irish investigators in Cork have spent 2 years developing a better device. And now, Donagh runs his materials through rigorous testing ahead of a critical review of their work at Europe's Space Technology Centre near Amsterdam.
We're doing a high temperature storage test over a period of several hundred hours. This is typical of much of the testing we do, and even in the European Space Agency. You make a device, you put it under a certain stress condition, and you monitor how its electrical characteristics are changing over time. Yeah, we'll see how these guys look. These are some of the diodes that we've been fabricating ourselves. It's silicon carbide, and these silver tapes are used to interconnect with the solar cell. What we'll do is we'll take them up to the electrical test lab, and we'll see if they're losing efficiency or it's staying the same. When you consider the amount of planning that goes into a mission like this and the amount of the cost as well, they really can't afford a failure to happen, because if these switches fail, the solar panel on the satellite can't effectively generate power to drive all the components on the satellite. So there's a possibility that some of the critical devices on the satellite would also fail. And there's a lot of time and effort wasted on a mission. Some of the initial results look promising, all right. We've done 1,000 hours storage tests at 350 Celsius. We'll probably have to make some improvements, but I think it's all down to the review meeting now. In a few weeks' time, we'll meet the rest of the project partners, and we'll come to a decision on whether our devices can be taken on to the next phase of the project. There's a chance that even these materials could fly in space, which would be a major achievement for an institute like ours. Fingers crossed. Let's see how it goes.
Being successful in space technology isn't like being successful in consumer goods, for instance, because the level of reliability that's required of industries in the space business is so much higher. But of course, what happens then is that companies who become that good that they can send their products into space build better consumer products.
Meanwhile, Donagh, having returned home from Holland, has just received word on the outcome of their materials review meeting.
So, Donagh, what's the news? The news is good. We passed the review stage. This basically means we get more time, and I guess more importantly, we get more money to keep on developing the technology. So it was a good day all around. Okay, the next stage for us is we have 6 months to iron out some of the technical issues that arose. At that stage, we really have to show that the technology is at a mature enough stage to go into a space-qualified test campaign. So there are some small issues, but I think we can manage that within the 6-month time frame. If we can demonstrate that these devices can operate in the environment that this mission will experience, then it demonstrates that the technology can take over from silicon, which has been there for almost 50 years. It opens up a lot of other possibilities as well, not only in space, but for applications on the ground as well.
Irish investigators are competing with some of the finest researchers in the world in a global enterprise to understand the universe, and, just as important, to bring that same technology home. As research teams across the country push the boundaries of our knowledge, they're making us stronger and better able to compete in a new technological world.